Hello. Today I would talk about a different kind of computing as what we are used to with our laptops and phones. That's a form of computing that's very inspired from uh, the way the brain actually treats information. And so that's what we call the broad field of neuromorphic computing. And since this is a nanoscience class, I will discuss some implementations of it that were made using Spintronics. Um, so first, let's start with a bit of neuroscience, because since we are taking a lot of inspiration from the principles of neuroscience, it's good to know a bit what it does. So in the brain, um, the main, the basic processing unit is the neuron, and it does the integration of information locally as well as storing the information locally. The way it works is that when a signal arrives to the cell membrane at this spot, it induces an electric potential on the membrane, which propagates and decays over distance and time. And there's a very specific zone, like in the neuron, which we call the axon initial segment, at which if you have enough potential building up at this specific area, it will trigger a massive flow of ion into the cell, which is going to create a very large impulse wave, which will travel along the length of this output uh, appendix, this output, which we call the axon. Um, so when the signal reaches the end of the axon, it does what is called a synapse onto the next neuron, and essentially the strength of the synapse is depends on these channels, which is not relevant what they do, but it is relevant to know that there is a change um, uh, that's linked to those synapses and those channels. And that's how memory is encoded in the brain. So we actually want to use these principles, and there are many more, but mainly these two, to create a new topology of the brain, um, a new topology of computers which mimic that of the brain, where you have different areas that locally integrate information and communicate in between themselves. And also the morphology of the neuron, which has its memory stored at the same place as its integration center, whereas normal computers have the memory all in one block away and all its processing units in one other block, another spot. And the reason why it's important is because we are actually, like, AI, as it's done today, does the same thing, tries to do the same functions as the brain do, but it does so with a lot of more energy spendings. Like it uses a lot more energy. And so we want to minimize this cost. And one way is to take inspiration from the brain, because the brain, it runs on 20 watts. So it's really not much. And it's still capable of doing a lot of tasks, of pattern recognition tasks, and of dynamic learning tasks, which could be very interesting for AI systems. Um, there are some computational systems which try to emulate this. For example, Spinnaker at Manchester, of which this is a picture, but it is still electronics. We are still using logic gates and memory blocks to emulate, in a sense, neurons and synapses. And it does take a lot of space. It does still take, even if it's better, it does take a lot of energy. And so we'd want to do a we want to create a physical device which emulates the neuron and which we could scale up and actually do some pattern recognition or AI tasks that we're currently doing with some regular electronics. So what are Spintronics? Because I said we're going to implement neuromorphic computing on Spintronics. Well, there's many ways to go about this. Essentially using the polarization of electron spin to store information or create different behaviors and how our system operates. Specifically for this one, the research I was looking into was using magnetic tunneling junctions, which were discussed earlier in the course. And one interesting thing is that they show hysteresis where they have like a radical a switching event, which changes their behavior, and we can use this to actually model the fact that at some threshold level the neuron fires and there's a binary event in it's an axon potential, like it's a action potential traveling down the axon in neuroscience, but here it's the conductivity changing. So but there's a parallel to use here, and that's the idea. um in more details, we were trying to use spin transfer torque as a phenomenon to induce those switching events in the magnetic tunneling junctions. So what is this? It's essentially spin transfer torque is essentially the fact that you can impart a spin moment onto electrons by passing it through a fixed layer, like a magnetic layer with a fixed moment. And so this will polarize all the electrons in a similar fashion. And when they hit a free layer, well, the torque, the magnetic moment of that free layer responds to the torque, to the electron moment, like electron moment, and there's actually torque that's being imparted. And here we can see that if the torque is too small, well, the free layer magnetic moment is going to decay to its original state. But if it becomes large and actually reaches a threshold, it switches around and induces this radical change event. And this figure here just shows how we would expect the nano oscillator, like the spin transfer torque oscillator, to work, to look like. And so what has been done is that using we have been able to classify digits, spoken digits, using this kind of techniques. So the idea is to pre-process the input and to take from a sound to and pass it to a nano oscillator, and through this extract some information about what was the sound. So the two diagrams here show what happens with different kinds of filtering of pre-processing. Spectrogram is basically a Fourier transform, and cochlear is the cochlea is the sensory organ in the inner ear of the biology, but it's essentially a more nonlinear approach to I won't go into detail just now. But it does help for this is the results without the oscillator layer. And then later there was another experiment done where they could couple like a bunch of nano oscillators, and essentially what it shows is that yes, regular multilayer perceptrons are much better at doing this task, but they require a lot more training, like lot more training data than this neuromorphic approach. And that kind of correlates what the brain is. The brain does. It has very few examples to learn from, but it does it quickly. It's not perfect, but it's good, and that's what we want to emulate. And so what are the perspectives for this technology is we'd want to scale it up and like have millions of components and actually do some meaningful tasks, because the two first examples I showed were only like toy systems. Um, there are challenges with scaling it up, because it's not trivial to actually couple these oscillators together. One idea is to just use regular CMOS technologies and record what happens at some place and then send the input somewhere else. But we don't want to have too much overhead, because then it kills the purpose of not using too much electricity and energy. Some other proposed ways we're essentially using like MRAMs, which are magnetic random access memories, to encode have a connectivity matrix which encodes the inputs from a set of neurons to the outputs to another set of neurons, and those are all bits which can like um, specify the connectivity between our neurons. So those are all ideas. They have not been put in place, but it's a worthwhile to talk about. Another issue with that is that um, the systems we are using are inherently like stochastic, and they tend to give varying answers, varying outputs. But personally, I think that it's not so much a problem as a feature, because when we look at how the brain does its learning, and we're all running on the same hardware, but we have widely different responses and answers, and um, it's kind of how the brain operates. So the fact that the physical systems we're modeling are stochastic is, in my opinion, not a big issue. For some people, it is. Thank you very much. Those are my references for this article.